Hi, sir.
Hello, Amy. How are you doing?
I'm very well, thank you. How are you?
Very good, very good. So last time we discussed about the inequalities. We mainly
Right.
focused on linear inequalities. So is that part absolutely clear to you?
Yes.
We introduced a bit about absolute function inequality. That was also clear to you, right?
Yep.
Few things which I thought we'll again take up, which is involving absolute function with nonlinear inequalities. Today, we'll actually discuss nonlinear inequalities, okay? Any difficulties so far, Amy?
Um, there were a couple of questions, but I sent them to you through WhatsApp.
Okay. Okay.
Yeah.
Yeah, we'll take up those questions in nonlinear inequalities because they were related to this particular topic. And I hope
Okay.
after that, everything will be absolutely clear. Okay.
Mhm.
I plan to have a test next time on this particular topic. And then let's move forward from there to a new topic. Okay.
All right.
Let me share the screen with you. This is what we have prepared for you. So I hope you can see the screen.
Yep.
Right. So these inequalities are with nonlinear functions. So we'll today discuss about inequalities which will involve quadratic functions, polynomials. Well, quadratic functions are also polynomials. We'll take cubic functions. Reciprocal functions, rational functions. Again, reciprocal functions are also rational functions.
Mhm.
But there is slight difference in simple rational functions and the complicated rational functions. We'll discuss how they're different while solving inequalities. Now, all these inequalities till now, which we had been discussing, were involving one variable x, and therefore our answer was based on whether x is between some interval or it is beyond some interval, correct? That is how we were saying was the solution to our inequality. Now we'll consider two variable system also in which we'll have a coordinate plane, a graph on that, and the solution will be a region instead of just the domain of x, okay? And then we'll have a practice question based on exam review. Now, before jumping into nonlinear inequalities, I want to focus on one particular thing which is very critical in solution of nonlinear inequalities, and which is what is square root of x squared, I mean?
Absolute value of x.
Perfect. That is so critical. So if you do that mistake, then most of the solutions can go wrong, especially when you're dealing with algebraic solution to quadratic inequalities. Okay.
Right.
So some techniques which we are also going to focus while solving these questions involve absolute function operations, which we also looked into earlier. We'll also see interval table analysis and also how to shape the graph to find solution for two variable systems. Perfect.
Mhm.
So let's begin with the quadratic function itself. Now, a quadratic function could be given to you in many different forms. You could write a quadratic function standard form, you could write that in vertex form or in the factored form. Now,
Mhm.
in an examination, it could be any of these forms. So my examples will consider one of each kind so that, it gives you an idea how to solve inequalities when we have quadratic functions of a different kind or of a particular kind, okay? So the very
Okay.
first one is to solve a factored form of quadratic equation, which is x plus 3 times x minus 1 less than equal to 0, right? So that is what we
Mhm.
have. Now here, as you can see, I will discuss two methods with you, method 1 and method 2. Method 1 is by sketching a graph, and method 2 is to analyze interval table for sine. Now, these two methods are very general methods to solve any inequality. So as we move along, the methods which we are discussing now will be very useful, correct?
Yep.
Now, when you want to sketch the graph, you're already given a function in the factored form. What is the best way to do it? Tell me,
So I would find the zeros.
correct?
And then since it's less than or equal to, I would know it's the x would be in between the two values,
Perfect.
both being included.
The inequality solution is right there before you. And what you're saying is absolutely right. So when we are really sketching a graph to solve an inequality, we're not really interested in where the vertex is, right? It could be anywhere,
Right.
right? We're only interested, as MEU said, on finding out where the zeros are, which are absolutely clear from the factored form. We know we have a zero at x equals to -3 and another zero at x equals to 1. A second important thing always to notice is the coefficient, the leading coefficient, right? So that is kind of very critical before jumping into the solution. Now, in this particular case, you can see the leading coefficient of x is +1, and this x is also +1. So when you multiply, we know that the leading coefficient is positive, correct? So first thing is, when we notice here is the leading coefficient, which is, we are saying leading coefficient is positive. It means really that the parabola will open up, correct? So parabola opens up, perfect. And now we already know the two zeros, right? So we know the two zeros, and therefore we know the solution lies in between. Perfect, so simple as that. Now, I mean, since you identified these are the two zeros, and since the inequality involves less than equal to, that means you will include both these zeros. Perfect. Including both these zeros, you can write the solution in many different forms, correct? One of the form could be to write in the set form as shown here, where we put the curly brackets, x belongs to real numbers, so that x is greater than equal to -3 and less than equal to 1. Absolutely clear. This is a very fast way of answering this particular question, and you can always use this strategy, especially to answer a multiple choice question within a minute or so, right? Clear.
Yeah.
Now let's look into a more exhausting way of answering, right? But that is very critical when you have complicated equations and things are not that simple. So a simple example is a good idea, I mean, to understand complicated methods also, right? Do you agree with me?
Yeah, definitely.
So let's take the complications involved. So what we are now going to do is, we'll again begin with the function itself. We are saying the function is x plus 3 times x minus 1. First thing, always find the zeros. Once you find the zeros, there are two zeros. Two zeros are going to divide the whole plane into three regions, correct? So we make our table with zeros. We have two zeros. When you put those zeros there, it divides the whole coordinate plane into three intervals. So the zero at -3, left side will be minus infinity to -3. And between the two zeros, the region is -3 to 1. And beyond the other zero, it is 1 to infinity. Once you have your intervals defined, which I can show you here, so we have these three intervals, correct? We need to only figure out where do we have a negative value, since we are focusing on less than equal to, correct? Not the value, negative value. That is what we are interested in. And therefore, what we do is that at each interval, we just take a point, one test point in each interval, just to see the sign of our factors, correct? You know, only at 0, the curve will change the sign, correct? Once it changes the sign, it has to go up to the next 0 to change the sign. So that's the whole idea. So why not just focus on the three regions which we have, take a point, and then we'll have the whole idea about the region from one point itself, whether it is positive or negative. So the two factors involved here are x plus 3 and x minus 1. And for both these, all three regions, we have the signs written in the table itself as shown here. Perfect. The function inequality which we're looking into is the product of these two factors less than equal to 0. When you multiply two negative signs, you get positive. And when there are odd number of signs of negative when multiplied, you get negative. We are looking for negative answers, and clearly the region between -3 and 1 is our interest. So we got this particular region. So once you have identified the region, you have to look back into your boundaries, right? So let me focus here of splitting the question as finding the interval and then concentrating about boundaries. Well, we see it is less than equal to. That means we have to include it. So fill in Those boundaries also include them and write them clearly in your solution. So in this particular case, as you can see, we have used a different convention of writing the solution. The square brackets here indicate included, right? So square brackets -3 to 1 means we have an interval including -3 and 1 and everything in between. Is that absolutely clear to you, Amy?
Yes, sir.
Perfect. So note here is the x-intercept will be part of the solution as the inequality is less than and equal to, right? But my advice to you here is that even after solving the question, you're clear about the region, right? In between, go back and look into your question and see what was the inequality, right? Because
All right.
the whole rush of solving, sometimes we forget what we were solving for, correct?
Yeah.
So again, focus and see, okay, it is less than equal to. So this is perfect region to work with, and let's fill in our boundaries and take the whole interval. Perfect?
Yep.
So we learned two important methods to solve nonlinear inequalities. Let's move on to the next type of quadratic function, and this time we have kind of a standard equation, right? So we need to solve the inequality, which is 12 minus 4x minus x squared greater than equal to 0. That's the inequality. Now, to solve an inequality involving quadratic function in standard form, the best way is to complete the squares and write it in the vertex form. Do you agree with me? You should
Yeah.
complete. Otherwise, you cannot solve it because we need to isolate x. You understand?
All right. Okay. Yeah.
I agree with you on one point. You want to say you could factor this, correct?
Yeah. You knew I was going to say.
I could guess that. Yes, Evie. You could factor this, no doubt about it. You could factor this. And the simple examples which I'm taking, you can definitely factor them, right? But believe me, in the examination, if they give you an equation in standard form, it might be not possible to factor. It may not have
Oh, okay.
integer zeros. It may not have integer zeros. Is that clear to you?
All right. Okay.
Sometimes our reason for give you an equation like that, which will be worth like more than 4 marks, will be to test you out on other capabilities of solving an inequality. Okay?
Oh, okay.
So remember, if you're lucky, you'll get a simple, factorable form, but I won't give you a factorable form. Well, for the purpose of the video, as you know, I've taken a very simple example, but definitely it is far, far, far from the examination question. Okay, we'll get back to examination questions tomorrow. Remember, my standard equation will not be easily factorable. Okay.
All right. Yeah.
Now, we need to complete the squares to find the answer for this. You remember the completing the squares method, Amy?
Yeah. So that's when you take the coefficient, you divide it by 2, and then you add, you square it by adding and then subtracting it.
Absolutely right. That is what you do. Second thing you will also notice here, what I did was, we have this particular function 12 minus 4x minus x squared greater than equal to 0. First thing which I did was get rid of this leading coefficient which was negative. You see that? So that is very, very important. Now, whenever I'm teaching you these inequalities, my focus is that the leading coefficient should be positive, right? So that is the note given here. Write the inequality with positive leading coefficient and then solve. So first step, make the leading coefficient positive. Once you make the leading coefficient positive, you know that the parabola will open up, correct? So you are looking at the parabola which is opening up for sure. Now you can apply the strategies learned that if you find the zeros, in between means less than and outside means greater than. Very simple, beyond. So it becomes very simple. So let's be very clear about it. So first step, which I've gone through here, is making the leading coefficient positive. Now we move forward. Well, you could have factored this. I'm not saying that. 6 and 2 are easy factors, right? But we are going to follow the completing the squares method. Since with these examples, we do understand complicated methods. That's the policy, correct? Okay. So as Amy, you were saying, half of 4 is 2, 2 squared is being added and subtracted, and that makes x plus 2 whole square as a perfect square. On the other hand, we have minus 16. Taking minus 16 to the other side, we get plus 16. And now comes the critical step. We have x plus 2 whole square less than equal to 16. What will you do next, Emmy? Tell me.
So what you did on the first slide, so the square root of x plus 2 whole squared would
Yes,
be the absolute value of, so within x plus 2.
perfect. So you'll do square root both sides, no problems on that step. However, what is square root of x plus 2 whole square? It is not x plus 2. If you do that, you made a mistake.
Right.
This absolute value of x plus 2, that is critical. So we are saying now that the absolute value of x plus 2 is less than equal to square root of 16, which is 4. Within means within, right? And including boundary, because it is less than equal to, and therefore we have a solution that x plus 2 is within -4, -4 and +4, correct? And that is the value of x plus 2. And
Oh,
great, we got this solution. Do you see that part?
yeah. And
This,
then we can work from there.
this is the best solution for that question. And it is not discussed in many books. Let me emphasize on this particular step. Once again, you'll not find this step in many books, okay?
Wait, so does this completing the square work with all quadratic equations?
Yes, it works with all. You remember that formula, x equals to minus b plus minus square root of b square minus 4ac?
Yeah. Do you not have to use that then?
It is derived from completing the squares.
Oh.
Yes. So it is only derived from completing the squares. So be ready for a test question on the same. Okay.
Oh, so quick thing. If you ever had to like get it into a form like this, let's say, instead of doing the whole minus b whole squared thing, you can do it like this and then work from there.
Yeah, clear?
Yeah, and that's really easy actually. Like just because obviously in this case it was nice easy numbers. Like you said, when it comes to obviously numbers which can't be factored, it immediately gives it into the form that the inequality should be either within or like the two separate ones. Immediately it's given like that. You don't have to do any like conversions or anything. Yeah, it's so cool.
It's the best method, I mean. And I'm really surprised why many books do not have this. They should start from here, right?
Yeah. They want to make it harder for us.
Yes, because they leave it for the examination, right?
Yeah.
So we have a simple solution from here that the absolute value is within a number. That means it is within plus and minus of that number, right? And this number happens to be 4. So x plus 2 is within 4. Now to solve this double inequality, we'll take away 2 from all the 3 terms and we land up with -6 on one side and 2 on the other side. Both are included, and therefore we have a solution within -6 and 2 both included. As shown here in the figure also, you can see that the circles are filled in to show that that is the interval, which is the solution for this particular example. Is this clear to you?
Yeah.
Absolutely clear, okay? Now, let's take another example moving forward with our nonlinear functions. Now, this is a different kind of equation, same base, which is quadratic function, right? So example 3a is quadratic and linear function. Solve the inequality x squared minus 4x plus 3 greater than x minus 1, okay? Now, I've written 3a since I want to discuss with you more than one method of solving such an inequality. Amy, can you tell me if this question comes to you, how will you solve it?
Right, so I would take everything that's on the right-hand side, so the linear function, which is x minus 1. I'll bring it to the left-hand side and make the whole thing greater than 0.
Perfect.
And then I know I'm dealing with, my answer should be like 2 different sets because it's like away from the boundary.
Okay, good. Perfect job. And so you'll follow the method which we adopted in example 1 and 2 to be very precise. Correct. Brilliant. Yeah. And this is what you should be doing, okay? Now, idea here is to also teach you different methods. And that is the reason why I've taken examples after examples, not to waste your time with one type of example, 100 times. Okay? It's not that kind of a lesson, okay? So here we learn something more, different technique of answering this particular question, right? What you said is perfectly fine. When you bring this linear part to the other side, becomes all a quadratic function, you could do factoring or you could do the completing the squares method, analyze and then answer. Perfect. Many times we tell you that this question will be solved by this process, and there you're restricted. So here,
Right. Yeah.
this question could be given to you in this fashion, that this is the inequality, graph the two sides, find the point of intersection, write down the solution of the inequality. So we have 3 points, A, B, and C. Perfect. First is graph f of x and g of x. They'll name them, right? They'll say, well, the left side is f of x, right side is g of x. It'll be more complicated than what I'm giving you, right? And then they'll say, the inequality is f of x is greater than g of x. A, find the point of intersection between f of x and g of x. B, shade the region where f of x is greater than g of x. C, write down the solution of the inequality f of x is greater than g of x. You get the idea.
Okay, yeah.
Think in those terms, and this is practically the same question, right? The only thing is, I've just put it in a simple form, okay? So 3A, find the point of intersection and write the solution. That is my question, right? So
Yeah.
when you have two different functions, it could be anything. In this case, it was a parabola and a linear function. You would have done it with the previous method, but it could be any other function also, right? I think there are two functions. First thing is, we are trying to find the inequality, the region which satisfies the inequality. So first thing is, where are they same, right?
Yeah.
First find where are they same. So that is what we'll do. Find the point of intersection means it's common to both, and then we'll move forward. So definitely, instead of solving inequality first, we'll solve the equation first, right? So we'll say this equals to that, and we solve that, and we get a point of intersection. First point. Is that clear to you?
Yeah.
Right. Now, sometimes we'll also say graph the functions, right? You learned all that. So in that case, you can just draw the graph. We have a parabola and a line, both of them there. And now we actually have some additional information. We know what these 2 points are, where they're intersecting. Okay. So we have those 2 points. Now, if the question asks for shade the region where the parabola has a higher value, then you know I've just shaded this in orange, showing that in those intervals, parabola has higher value. Once you have shaded and done all this, inequality is only asking for greater than. Since it is greater than, it's beyond, not including the zeros. And therefore, we have our solution, which is given right there. Is that clear to you?
Yeah.
Perfect. That is how you could easily solve the equation by graphing. Is that clear?
All right. Okay, yeah.
Now, important thing here is when you are graphing, sometimes you may not get accurate values, right? But if an example is something which I'm showing you here, where we have integer values as your in point of intersections, they're accurate enough, correct? They're accurate enough.
Yeah.
Straight from the graph, you can get your points and solve. So only this part can work in the examination if they have not put any other restriction. However, if it's not very easy to read from the graph, then what to do? Then you have to solve, right? Imagine if my answer was 2/3, then I should have taken the value from the graph. Is that clear to you, right?
Yeah.
So those are critical things which you have to think about, because in examination, apart from solving, you're also looking into time. So as the time is going past, it is not going to return, right? It's just one way.
Right.
So
Yeah.
you have to decide there and then what to do and what not to do. So if you read from the graph, do not do this.
So if you want a graph, is the only if you have, let's say, like two functions that you can sketch, can you do you only need the points of intersection as the only point of for accuracy?
Yes.
Or is there anything else you need?
No, only point of intersection. So
okay, and then you get an accurate answer.
Yeah, this was a much simpler example, Amy, because see, x minus 1 is such a straight, simple line, right?
Right. Yeah.
And then the parabola which I have taken is easily factorable.
Factored.
So is it easily factorable or not? I'm not sure about, but I think it is. Therefore, we got these 2 points also, right? So -3 and -1, correct? So easily factorable. So I could actually easily sketch my parabola as well as the line, and you know what? Even the point is common, right? So it's like simple to do. So for such a simple question, my graph was accurate enough. Perfect.
Okay.
But just think that that was not so simple, right? Just think this was not factorable, but once you bring it something additional, it becomes factorable.
Yeah.
That could be the situation. Is that okay? So
Yeah.
when we are looking into examples, just be more broad-minded and then see from different angles. What is this method teaching you? Okay, not
Mm-hmm.
that, well, this was so simple, I could have applied example number 1 and I was done with it. Right?
Yeah.
So it's for a purpose. Perfect.
Yep.
Next example is what? Oh, you see that familiar interval chart once again. Perfect.
Mm-hmm.
Now, Emmy, this time we are again solving the same inequality, and the solution means analyze sign with interval table after finding x-intercepts. Correct. That is what my strategy now is. Finding x-intercepts really means that I'm actually going to do, as you said, bring the terms to the same side. Is that okay? So I've
Mm-hmm.
now followed the method which you were saying earlier, bring x minus 1 to the left side. When I brought it, it got factored, and then we got the zeros. Those are the x-intercepts which we are talking about. And we are interested in finding a region which is our solution greater than 0. Greater than 0 clearly means we should not be including the zeros, and beyond is our answer. As shown here, the orange portion is your solution. We are done with it. Perfect.
Right.
Sometimes you may require to test your values using the sign table, correct? So as we said earlier, we have 2 zeros, and these 2 zeros divide the region into 3 portions. You can analyze your factors, taking the test points, check the sign. And the signs clearly indicate for x less than 1 and for x greater than 1, we have positive regions, and therefore the solution is x less than 1 or x greater than 4. Is that clear to you?
Yeah.
So it is not necessary for this question to do this part. So let me put a cross here. But imagine if this was slightly more complicated question, it was a cubic function, for example, or something else, right? Where the interval table could have worked better. Is that clear to you?
Yeah.
Right? For accuracy. So the whole purpose here to teach you a new method is to apply it when you have a complicated question, right?
Yeah.
Okay, now here is question number 4. And now this is the type of question which you wanted to know from me. And so I included this into my set of solutions. So the question here is, can you please read the question for me?
Yes. So example 4, solution in form of inequality. The equation kx squared minus 2kx plus 3 equals 0 has no real solution. Write the range of values for the k in the form of inequality.
Correct. Beautiful question, Amy. Thanks for sharing such things. Now here's the reverse way, right? So we are given the equation which is an equation, right?
Mm-hmm.
And saying no real solution. Write the range of values for k in the form of an inequality. Perfect. So the idea here is we have learned already that we have to analyze the discriminant b squared minus 4ac. Now, since we have no real solution, that means within that square root, we have a negative number, right?
Right.
So
Yeah.
b squared minus 4ac should be less than 0. That is what it is. So from the given equation, we have to identify what a, b, and c are. In this particular case, where the equation is kx squared minus 2kx plus 3 equals to 0, a is k, b is minus 2k, and c is 3.
Mm-hmm.
When you substitute these values, for b squared minus 4ac, you get this particular inequality less than 0 because we do not want any real solution. Perfect. Now, when you solve this, it can be factored as 4k times k minus 3 less than 0. That means we have a leading coefficient positive, right? K is positive.
Mm-hmm.
So it is a parabola which is opening up as shown to you. Now, can you tell me the solution of this particular inequality, Amy?
Yeah, so this is what I did, and then it was wrong, but I'm just going to go through it again, what I did. So yes. The 2 zeros I said was k equals to 0 and k equals to 3.
Correct.
But the thing with what I did was when it says no real solution, I thought it was b squared minus 4ac less than or equal to 0. Not just less than 0. So because I did less than and equal to, I included both 0 and 3.
Okay. Now, that was also wrong. And another thing is, I'm sure many students will make a mistake here. Now, look here. Now it is less than 0, you're clear about it. When it is less than 0, what should be your solution? Tell me. We have two zeros at 0 and minus 3.
Within 0 and 3.
So within 0 and 3, correct? That is your solution. Now you remember initially when I said we define the region from all this, but we have to look back at the boundary, correct? That was a very important statement. So our boundary is 0 and 3. Do you see that?
Yeah.
Now, the question is, should they be included or should they not be included? Well, most of the time they're not included, so we just go with the flow, write the answer, move out, correct? Now, in examination type of test question, they might catch you there, right? Now see the equation. If I put one thing, let me point out two things here. One is it says equation. It is not saying any quadratic equation. Does it say quadratic? No. It says an equation. It could be any equation, right? Now, I'm saying why quadratic. I'll explain you that part also. So if I put k as 0, this term becomes 0, right? This term becomes 0. What do I get? I get 3 equals to 0, right?
Yeah.
Is 3 equals to 0 a solution? No.
No.
That is what we need. Not a solution.
Oh.
It's not a solution, right? So we have no solution for even x k equals to 0. Therefore, the value of k can be included. You get the idea.
What happened if you sub 3 in?
3 what? Okay. So if you sub 3 then just see, you get 0 because then it is 0 equals to 0 because 3 is a 0.
That's a solution, right?
Yeah, that's the solution. 0.
Oh, so you can't include 3.
You can't include 3.
Oh, that's why it's only less than. Okay. Whoa. That's so cunning.
Killer. This is the killer because, you know, in multiple choice, I can give you all 4 choices, not including this and that. All those choices will make you crazy. You'll never get the right answer. Excellent question. Very difficult. Now, let me give you a word of caution here. If the equation says quadratic, okay, if it says quadratic, right, that really means that k is not equal to 0. Because if I put k equals to 0, it is not a quadratic equation.
Oh.
Got the idea?
Yeah.
Read the question. An equation or the quadratic equation makes huge difference. If I write a quadratic equation, leading coefficient is never equal to 0, never put it 0.
Oh, okay.
Perfect.
Yeah.
Make a note, right? These are few such fine points which, you know, 90 plus. When you're looking into something closer to 100%, these are the points to focus on. These are the places where people are missing marks and then all are not 90 plus, right? If you just points, you're surely above that. Perfect. Now we'll get to cubic function, which again I've taken a very simple example, okay, but gives you some concept. Can you please read the question and explain the solution since it is similar to the previous solution?
Yep. So polynomial inequality in factored form. Solve x times x plus 2 bracket times x minus 3 greater than 0. I would, start by graphing it.
Okay,
perfect. I know how to graph polynomials.
You know. So you'll find the zeros and graph it because you know the leading coefficient is positive, right side up, right?
Yeah.
Correct.
The degree is 3, so opposite ends.
And there you go. You have the solution. If you do like that, perfect, perfect. If there are no restrictions on the question itself, then it is perfectly fine, right? Now, sometimes in the examination, what we have is we have a cubic function which needs to be factored. So remember, you may have a cubic function which is not factored for you. So then you do trial and error, get the first factor, then you do the synthetic division or long division, get the other factors. So first step will be to find the factors of the cubic equation. Once you have the factors, then they will say, analyze it using the interval table. Then this is how you're going to do it. You, in
Oh,
this particular case, we have 3 zeros. And so they're going to divide the whole region into 4 intervals, write down your factors, take the test point and check for their positive and negative value. Even number of negatives will give you positive, odd number of negatives will give you negative. Since you're looking for greater than 0, answer will be everything which leads to a positive region. And that becomes in the form union, right? So when you write this particular solution, boundaries are not included since it is greater than 0, right? And then it's union, or you can write or also, correct? So that is how you're going to do it. So the graph shown here really confirms that is the right answer, right? But if the restrictions are not there with you, and the question is as simple as taken in this example, you can just graph, write the answer, and move on. Perfect.
yeah.
Yes. Question number 6, we are taking now a rational inequality. And the question here is to solve 5 over x minus 3 less than 2. Now, when you have this rational inequality, we have always restrictions. So the restriction is that the denominator cannot be equal to 0. And therefore, we have written, it should be written, x is not equal to 3. Very simple. Now, if I give you this equation to solve, how will you go about and how will you solve this type of an inequality?
Right. So yeah, I'll do what you did first, write down the restrictions, and then I would bring the 2 to the left-hand side, make it all less than 0.
Correct.
Make the denominator x minus 3, and then they would be, it would get into like a factored form, and then I'll just use the interval table and then work from there.
Beautiful. So that is just the right method to do this type of question. 5 over x minus 3, what Emmy you're saying is bring down this 2 and we get this. And then we have a common denominator of x minus 3 and we are writing this as 5 minus 2 times x minus 3 and we are saying this is less than 0. Now we can simplify the numerator. We say 5 minus 2x plus 6 over x minus 3. Correct? This is what you're going to do, correct?
Yeah.
So you have now here minus 2x, and when you combine these two terms, you get plus 11 here, and you have x minus 3 less than 0. And once you have that, use the interval table and write down your answer. Remember,
and then look for a negative because it's less than 0.
Agreed. That is how you should be doing. Perfectly fine. And that is the method which is normally adopted and is the correct method. Agreed.
Okay.
Perfect. Now, I just wanted to teach you a different strategy here, which we are going to use and see how simple it becomes many times to use an alternate method. So since we talked about all this, let me write down here alternate method. Is that clear?
Yep.
Okay. So now, Emmy, can I multiply by x minus 3 on both the sides and simplify and I'll get the answer?
Can you?
No. Can you?
I would have said yes.
You can.
But you said no.
So can you please read the first statement here?
Yeah. So you cannot multiply by x minus 3 on both the sides to solve this inequality.
Yes. Now, many times I've seen in test papers, what students will do, they have this inequality, they'll just multiply by x minus 3 and they have a linear equation to solve and immediately in no time they'll get the solution, which will be wrong, of course. Now tell me, why can you not multiply by x minus 3 on both the sides?
That's what I would have done, so I don't know.
Okay, so look here, the next statement is multiply by x minus 3 whole square. So the next statement here is multiply by x minus 3 whole square on both the sides, since that will always be positive. Now, does that remind you of something? Not
like
but x minus 3 whole square. So does it make sense? Can you now tell me why you cannot multiply by x minus 3 on both the sides?
Oh, does it like come back to that thing that you were talking about, how the leading coefficient always needs to be positive? And if you use the square of it, it would always be positive. Whereas we can have, if you use x minus 3, it could be negative, and we don't want that. I don't know.
Okay. Yeah. So the reason here is, I mean, x minus 3 could have a positive value or could have a negative value, correct? Now, in inequalities, we learned in our last lesson that if you're multiplying by a negative value, I have to change the sign of inequality. I have to reverse the sign. But if you just multiply by x minus 3, how do you know where to reverse the sign? Because x minus 3 is not a positive number. It could be negative also. It could be 0 also. Well, x is not equal to 3, it will not be 0, but it could be negative or positive. However, x minus 3 whole square is always positive. So I can easily multiply both the sides and solve. Do you get the idea now?
Yeah, that makes so much sense.
So do not go for shortcuts multiplying by a linear function on both the sides, because the linear function will be negative also. Whenever you multiply by negative, you have to change the sign of inequality, and that makes huge difference. And therefore, I took up my second method to teach you this particular concept. And this concept is, do not multiply by x minus 3, but you can multiply x minus 3 whole square.
Whole squared.
It may look complicated, but it is what it is, correct? So that's what I did. I just multiplied by x minus 3 whole square on both the sides. This is always positive, so I can do it without changing my sign or bothering about the sign, right? We'll keep it same. Perfect. And now we have x minus 3 on both the sides. We bring it on one side. So I kept 2 times x minus 3 whole square. For a change, I brought my numbers on the right side, the expression, left 0 on the left side. Now see, at this stage also, we need not expand and simplify. X minus 3 is a common factor. So take x minus 3 as a common factor and then simplify. So it's not complicated. Do you understand?
Yeah.
Very important step to save time and to avoid mistakes. So I do x minus 3 as a common factor, and standard ways to write 0 on the right hand side. So I just rearranged and got my inequality. And I simplified and I got the factored form straight away. X minus 3 times 2x minus 11 greater than 0. You see that?
Yeah.
If you now see it, it is not more complicated than what you could have done otherwise. It's kind of similar steps.
Yeah.
And we easily got the factored form. And from there, we also get the same answer, which you could have got otherwise. Correct? So we are looking for a region which is beyond 0. Correct? And we also know that 3 is a restriction.
So can't include.
Yeah. Even if it was greater than equal to or less than equal to.
You can't. Yeah.
Right? And from the graph also we see clearly what the solution is, as shaded in orange, and it's very clearly written here with an OR statement. So you can write or union. Is that clear to you?
Yep.
Perfectly fine. So, Amy, what did you learn in this particular example?
So I learned that do not, if there's like a shortcut of like in this one especially, thinking if you can multiply by, let's say, the linear function, which is x minus 3, thinking you can just easily cancel it out. Don't do that, because we don't know whether x minus 3 is a positive number or a negative number. Because let's say, if you put 5 as x, you're going to get positive. Put it as 1, you get a negative number. Yeah. Whereas with x minus 3 whole squared, if you put it as 1, 5, or anything, it's always going to be positive. Okay. And that's the number we have to deal with when doing rational inequalities.
Perfect. That's how you're going to do it. And here is a simple example for you. You'll love this. So, Amy, can you solve this inequality for me? Read and write, tell me the solution.
Okay. So, solve 2 over x being greater than or equal to 1 over 4, where x is not equal to 0.
Yes. What will you do?
So, it's 2 over x. So, we can multiply both the sides by x squared.
Correct.
And then,
you understand this? This time you are not bringing 1 over 4 to the other side.
Yeah.
You're not saying 2 over x minus 1 over 4. You know that?
Oh, yeah, that's what I did before.
Do you understand?
Oh, no, yeah.
Both are correct. What I'm trying to say here is that, well, the method which you normally would adopt is 2 over x minus 1 over 4. And you got two fractions on one side. To deal with fractions is not so easy, correct? On the other hand, what you are doing now is you're multiplying by x squared. You find that more convenient and easy. Do you see that?
Yeah, it's like you changed my mindset, because now when I'm looking at a question like this, I'm trying to find how do I get rid of like the x, but do it in such a way it has to be that positive number being multiplied.
You are a good learner.
It's so much easier. Oh my God.
You are a good learner. I can say that. You immediately adopted the method which I've taught you, right?
I didn't realize I did.
That's the beauty. So you now appreciate how effective this strategy is to multiply by a square number on both the sides, or square expression on both the sides. It simplifies. You cross multiply by 4 also, right? I just kept 4 for a long period of time. There was no need. I could have just cross multiplied with 4 also, correct? My answer is, and actually I wanted to test you on that. The whole purpose of putting this question here was only to see what is your choice once I have told you.
Because both of them, like you said, require the same amount of working, but it's just which one's more convenient. I just find the other, like the one you just showed me, way more, like so much more better, because it easily cancels out the 2 over x, because it will become 2x, and then you can just work from there. And that's what we've been doing since the beginning. So I'm more familiar with that one.
You could have cross multiply with 4 also, and then get rid of 4. 4 was not really required. I mean, there's no need of 4, correct? So you can make it much more simpler. So basically, you're working with such a simple example now because you know the concept and you have the confidence. The multiplication was such a simple thing, which simplifies your actually expression. It doesn't complicate. And secondly, do not expand if you have an expression. Factor it out, right? So once you factor it out, again, you are working with a very simple equation. Clear?
Yeah.
So that is how you're going to solve this. And again, we have a solution, and definitely we have a restriction, which is x is not equal to 0. So always remember, x cannot be 0. Do not include that restriction in your answer. Is that clear to you? I've purposely taken greater than equal to, making you could have made a mistake, right? Greater than equal to.
Usually I would have seen that and I would just be like, oh, since it's greater than equal to, that's a sign to use throughout. But then that's why you always say write restrictions first, so you don't make that error.
Correct. Now, solving means getting the region. Now, writing the answer means check the boundary. So when you have this boundary of your region, you go and check, 0 doesn't fit in. So I do not have to take it. Do you agree with me on this?
Yes.
That is kind of important to understand. And so with that, let's move on to the next question. Okay? This is a real rational function, which I was saying, I was using different terms, reciprocal and rational. So when we talk about rational functions, we make it more complicated, right? This is kind of which we have, Amy. So given this expression, can you read and tell me your strategy to solve this question?
All right, okay. So solve 1 over 2x minus 2 being greater than or equal to 3 over x squared minus 1, where the restriction is x is not equal to plus or minus 1.
Okay. How will you do it?
So since it's not like a reciprocal kind of thing where we can do that x squared and simplify it, because the denominators are not like that, which can be easily simplified. So I think I'll just do the same method I did with the other rational function. I'll just move the 3 to the other side, and then interval.
You're going to do perfectly fine. So that is your strategy. You understand it fairly well. Bring it together, do all that factoring, and surely you will need interval table for this particular question, correct?
Right.
You cannot solve it without interval table easily. This is very important. And that is why we were taking this interval table with simpler examples, so that, if you complicate the situation, which is going to appear in examination, you have to use combined strategy. Algebraic solution, finding zeros and undefined points. We call them critical numbers. So we got 2 critical numbers, 2 types of critical numbers here. We have the zeros and we have the vertical asymptotes, which are beyond our domain. You can agree with me? Now, once we have all that, then we're looking into combined kind of intervals. In this case, we have 4 intervals to work with. Take your test points, multiply the factors, signs, and get your result. And then also, while writing your answer, which seems to be from -1 to 1, can you include -1 or 1? Clearly, it says you cannot. So do not include this, right? The next one is from 5 to infinity. Can I include 5? Yes, you can. And therefore, include it. I didn't include.
Square bracket.
No, yeah, square bracket 5. Do you see that? I found my own mistake. So it is important, these 2 steps are for a reason. You see my mistake here? So I did without including 5, which was a mistake, right? So another thing which I do normally is, when I'm looking at the zeros, which is 5, I actually put a 0 here, saying as a reminder that this should be included.
Yeah.
You're getting my point?
I've seen it in your videos, and then you put like a whole.
I put a circle here saying that these are the vertical asymptotes. Do you understand? So I don't do that. And this video explanation, at picking up the right examples, I missed it. And therefore, I want to really emphasize, you have got the region for the boundary. Check your question. See if boundary works. If it works, yes, include it. Right? Sometimes you've seen 0 worked last time, right? For the correct equation, right? Even when it was greater than. Next example is a different kind, Amy, which we'll extensively also see in some other exercise in a different unit, which will be for your year 13. But I thought at this moment to include this, just to give you an idea. So we have now question number, example 9a says, graph inequality with 2 variables. Till now, we were focusing only on the x. We were always saying y equals to something, y equals to something, but we kind of ignored y and we just worked with xx, right?
Yeah.
Many times what happens is the question is so specific that they want an interval with the region to be defined which satisfies the inequality, which means both x and y values. In that case, we have to shade a particular graph. So I've taken here 2 linear equations, and these linear equations are basically different kinds. Graph linear system, which includes 2 equations here. One has greater than equal to sign, the other one has less than sign. So when you graph, you draw a line. When I'm saying greater than equal to, means y region is above the line. And when I say greater than equal to, it means the line is included. So in this case, we have a solid line. Do you see that? So this particular thing is when we say y is greater than equal to. Is that clear to you?
All right. Okay.
On the other hand, if I have a condition which is less, in this case, I'll just write y less than something, correct? So when I have less than, then do you see that dotted line?
Oh, so not included.
Not included, right? This is solid, right? So that is kind of very important when you shade them. And of course, when you shade them, you want something which is in between, and clearly this portion is in between, so it gets shaded, double crossed, and that becomes your solution. Is that clear?
Right.
You have to find the point of intersections and then get your answer. Now, I've extended this question a bit more. This is with just a system with 2 equations. There could be more than 2 equations involved, Amy. So just to make it complicated but simple enough, I added such simple equations to my example.
Oh, love it.
So x greater than equal to 0, y greater than equal to 0 means I'm interested only in quadrant 1 now,
right?
Not in there. And therefore, I highlighted that area into a big solid triangle as my solution.
Yeah.
Do you like it?
Yeah, I do. I just wish the exam was like that.
Yeah, exam won't be like this, right? You'll get some trapezoid there or something, right? Some other figure which will be too complicated to find area of, right? So we extend this question and say, find the area of this region. You're getting my point, right?
Yeah.
So the question will be, find the area defined by this region, right? That is the complicated question, was 6 months, okay? So expect that sometimes.
Okay.
So with that, we almost end our lesson, but I'll not end there. I'll just have one more example for you, mainly to bring you back to your year 12. And this is what you're expecting in year 12. So can you please read the question and tell me how can you answer this examination style question?
All right. So example 10, inequality with nonlinear systems. So L1 has the equation y equals x plus 1. And L2 has the equation y equals x squared minus 5. A, find the coordinates of the points A and B, the points of intersection, and then write the solution for the inequality where x plus 1 is greater than or equal to x squared minus 5.
Okay.
And then B, shade the region that satisfies the inequality y greater than or equal to x squared minus 5 and y less than or equal to x plus 1.
Okay. So tell me, how will you solve it?
So A, find the coordinates points A and B. So simply just take the two equations, make them equal to each other, and then solve points of intersection. Once you find the x values, sub it in, find into the y equals x plus 1, because that's a simpler equation, and then find the y values, which you've done, and you've got A as 3, 4, and B as -2 and -1.
Correct.
So, yep. And then the second part is write the solution for the inequality where x plus 1 is greater than or equal to x squared minus 5,
Correct.
which means we're looking for, so this is the line, we're trying to look for where the line is above the curve, like the quadratic curve.
Right.
So that will be in between the 2 points. That we have just found, the points of intersection, because like it clearly shows with the graph, we can see that the line is obviously above those 2 points.
That is so true. Perfect. I missed a step while typing it here, and that step was definitely x squared minus 5 equals to x plus 1. And then you bring it together and then solve it, correct? So I missed that step in typing it out. So typing is a big problem for me. There's too much of work involved. Okay, so that is perfect. And you see, in examination type of question, there are different parts, and that is how they walk you through. And then, therefore, I was saying, emphasizing that you have to know each and every step. So here we are also asking you for shading the region, right? So it makes sense to take something from your year 13 and make you aware that this could be there in year 12 also. Is that clear to you?
Right, okay, yeah.
So that is the end of our lesson for today, pretty long lesson. Amy, I hope you understood something. Can you summarize what have you learned?
Yes. So we start with quadratic functions. Do you mind just quickly going through the slides? I'll just pick out the key points.
Okay, sure.
There was a lot, because there were so many alternate strategies and things you used that were so crucial. Yes. It's not good to know just one of them, because like you said throughout this whole lecture, there would be more complicated questions that would come in exams, and to use the right methods to get to quickly answer that question, because some are longer than others, some only work with ones that are factorable, so we need to know all these methods. So yeah, so the simple factored form, you can even do it without the table. You can just look at it, factor it out, and as we know, we need to make sure that the leading coefficient is positive, so we know it's concave up, and then it's less than or equal to, so we know it will be within, the x value will be within the 2 zeros. So yeah, that's nice. And then you can do it by graphically or using the interval table, but we will come across those later on.
Yes.
So the algebraic method. Oh yeah, so this one, this is the one I said that can be factored, but when it comes to more complicated ones which can't be factored, we always use the minus b plus or minus b squared minus 4ac over 2a equation. But to do this, instead of getting into all that fuss, which is a really long problem, do completing the square. And whenever in doubt or whenever you're stuck, just use completing the square, because it always works for every quadratic equation. So yeah, quite simple really. You take the coefficient of x, you divide it by 2, and then you square that by adding it and subtracting it. And yeah, like Sir just highlighted, the key point is the square root of x squared is the absolute value of x. Don't just write x, because that's wrong.
Yes.
Yeah.
Perfect.
And then graph, what's this one?
Fine, yeah. And then, we have the solution. You're right. Next method.
Yeah. Next one, so quadratic and linear functions. So yeah, this is quite simple. You have two different functions. So this was the one where I had a few methods. I did it by bringing everything on the right-hand side, moving it to the left-hand side, and simply solving it like that. But if it wasn't like that simple to do, you can do it visually by graphing it, and you know how to quickly sketch a graph. But the thing with graphing is make sure you've done it accurately. Otherwise, the points of intersection and things, they need to be accurate as well, because the values you're picking off the graph when saying if it's greater than, like let's say in this one, x is less than 1 and x is greater than 4, they are accurate values. So you need to make sure that you have an accurate graph to get those values. And then the next one would be the table of intervals. So yeah, again, the same question, but just showing alternate strategies to use to answer this question. Honestly, whichever one you prefer to do in the set time you choose, but it's good to have all these options available to you. Then what's next? So this question. Love this question. Right. So so with this one, it's the discriminant. We were talking about how when it says no real solution, we know the b squared minus 4ac is less than 0. And then when solving it, we're thinking, so what I thought was both will just be, so as the solution says, 0 is less than or equal to, but I thought it was just less than and then k and then less than 3. But the thing to note is after you've got that equation, always take your solutions and put it back and see, does it fit the defined boundary that you have set? Because like in this one, if you just left it as less than and then put 0, that's not right, because if you put 0 back into the equation they've given, so simply if you put 0 back in, you get 0 plus 0, then plus 3, and you get 3 equals to 0. And that's not a real solution, and that's what the question's asking. It's saying which one has no real solution. So therefore, 0 can be included.
Perfect.
Cubic, so this one's a polynomial. I love sketching polynomials, so I would always go for quick sketch of the graph and then work from there. But they can get more complicated with x cubed and so many other factors. So interval tables are the best option to choose when coming to polynomials, because it's very easy to just quickly put all the factored forms on the table. You don't even have to find the values. You just need to see whether the signs are positive or negative. And then according to whether it's greater than 0 or less than 0, you pick whether it's positive or negative.
Perfect.
The values.
Perfect.
Rational functions. So with rational functions, always write down the restrictions as your first step. Then you can, so later on I'll talk about how we can move everything from the right-hand side to the left-hand side. However, there are that you use that when they're really complicated kind of rational functions, when there's different denominators and it gets really confusing. Whereas this one, we have a nice whole number on one side and then a rational, like the function on the other side. So we can multiply both sides by x minus 3 whole squared. And that's a key. Don't try and do shortcut methods and do it by x minus 3 and then simplify, because x minus 3 could be a positive or negative number, whereas x minus 3 whole squared is always a positive number. So that's the one you have to use. Reciprocal functions, so again, you take that like an x squared or an x cubed, let's say if it was x squared at the bottom, always try and use those kind of, because in most reciprocal graphs you would use that method where you multiply both sides by like a degree above the denominator, I guess you can say like that.
Correct.
Yeah, so in this case,
you're right, even degree.
Even degree, that's the one.
Yeah.
Again, rational functions. Oh yes, so this is quite key. Again, writing the restrictions as we said. And in this case, because the denominators are a bit iffy, we moved everything to the left-hand side. And with the interval table, I really like the step where when you write down your zeros on the top and then you put your, the zeros, you have to fill in like a colored hole for where there are restrictions.
Yes.
No, sorry, a hole, like an open hole where there are restrictions and you can't use them, and then filled in hole where they can be included.
Correct.
Okay, yeah. And also make sure when you write your answer in the interval form, square brackets and curved brackets, even if it's the tiniest thing, that could change the whole answer. So make sure you get that right, because we can't afford to be losing these, 0.5 marks.
Yeah, because of the 0, we have to put a square bracket right there.
Right.
Perfect.
Yeah, so this was new to me compared with all the other questions, because we are dealing with 2 variables here, so not just x. Although it sounds all complicated, it's not that bad. Since so y we're saying is greater than or equal to, when graphing it, we try and use a solid line for greater than equal to, because that line and the results on it is included. If it's just less than or greater than, use a dotted line, because the results on that line aren't included, and then just work from there. Then this is another one, just developed the second part of the question where they could ask for like other graphs. So this, that way. And then finally, you've got inequality with nonlinear systems. So you've got 2 lines, and it pretty much works the same as we've done throughout, finding the points of intersection and things like that. And 0 test is very important, just to confirm whether there is a solution or not. So,
that is perfectly said. I hope with this, all the concepts are absolutely clear, Emmy, and you're ready for the test. So I'll like you to do all the questions from your book, share whatever difficulties you have, and from there we'll move on to the next lesson. Okay?
All right, cool.
So thanks a lot and all the best.
Thank you so much, sir. Have a good rest of your day.
You too. You too.
Thanks.